My name is Joshil Vaddi, and this is my lab for oscillations. Introduction. So the purpose of this lab is to compare the observed motion through tracker with the predicted motion or the computational model through GlowScript of a spring system. We want to determine whether or not the observed motion follows the energy principle, with the energy principle being that the energy is conserved and equals zero. This lab's conclusion will show that the spring system does follow the energy principle, and that is our brief preview. Let's look at some key concepts. Something important is Newton's second law, or F net is equal to mass and acceleration, which is also equal to delta p over delta t, which is the impulse equation. And what is also important is the velocity and position update formulas. R final equals R initial plus V average times delta t, and V final equals V initial plus F net over m times delta t. Now let's look at our spring and energy principles. So the kinetic energy is equal to 1/2 times the mass times velocity squared. The spring energy, which can be derived by the work done by the spring using the integral times r, can be written as S equals 1/2 ks squared, k being the spring constant, s being the distance it is compressed or stretched. We can also use a period for an oscillating spring, which we will show to find the period. This is T equals 2 pi times the square root of m over k. We also need to use a spring force equation, negative k times L minus L 0, L naught times U hat, and the energy equation, which is that the total energy of a system is equal to the work done by the surroundings plus the thermal energy that is exchanged between the system and the surroundings. Now let's look at the systems and surroundings. So in this case, the system is the earth, spring, and mass, and the surroundings is none. Therefore, there is no work done because there is no energy being transferred from the system to the surroundings and to the surroundings from the system. And the total energy is equal to the total energy of the system, which is a potential spring and kinetic energy combined. So in this case, it would be 1/2 times mv squared final minus v initial squared, which is the kinetic energy, the change in kinetic energy plus a change in gravitational energy, or mg delta y, plus a change in spring energy, which is 1/2 k s squared final minus s initial. Now let's look at the tracker. So for my tracker, I use a calibration skip with a fixed attachment point in order to calibrate the video properly and get all my data points, which follows an oscillation pattern. As you can see here, it oscillates back and forth in my x and y direction. Now let's look at my initial conditions. So I use 10.53 frames per second at 0.095 seconds. I started at frame 6, which is when the object was released, and my object mass is 0.402 kilograms. Our start time is 0, and our object's initial position is negative 0.102 in the x direction, negative 0.67 in the y direction, and 0 in the z direction. And our initial velocity is 0 for x, y, and z in all those directions. So let's look at the initial conditions. So I use my initial ball position and velocity, and then my time is equals 0, delta t equals 0.095, like I mentioned before. Our gravitational constant is 9.8, and our spring constant is 6.86, while the relaxed length of the spring is 0.126, which I actually found using these formulas. I used a period formula in order to obtain k by plugging in everything and solving for k. So I already had t and m and 2 pi as a constant. And then in order to solve for L naught, I used Fs equals mg, which is also equal to k times L minus L naught, which is the spring formula for the force. And using this, I solved for the L naught, which is 0.126 meters. Now let's look at the principles and iteration. So while the time is less than 5.5, I defined some of the initial energies like kinetic and gravitational, and then I found the gravitational force and spring force, and then subtracted them to find the net force. I then found the velocity of the ball and the position of the ball using the position and velocity update formulas. I then updated the spring using this, like L hat equals L divided by magnitude of L, and S equals magnitude of L minus L hat. And then in the bottom, I calculated the energies, and then I added them all up and found the change in energies. Next, let's look at the computational model. So this really shows how it all equals to 0, the change in energy. And you can see the oscillations between the delta K, the delta gravitational, and the delta spring energies. Let's look at the predicted versus observed comparisons. So here we can see that they're pretty similar, and there are some errors, like for example, the experiment doesn't have the peaks, and the troughs are a little too low. The peaks are a little too low as well. And this can be due to air resistance, friction between the mass, and the spring external forces. And this kind of oscillations occur because of how the spring moves from one end to the other keeping that constant oscillation going. So what does this mean? Well, the energy principle is satisfied because the sum of the kinetic energy and gravitational potential and spring potential energy equals zero, which is the total energy. So the total energy is zero, which means it satisfies the energy principle. Next, what does it mean? Well, the periods can be obtained for finding the time differences between the minimum or maximum between the time position graphs, which I found was 1.567 seconds and 1.432 seconds. And these are different because there are many other errors, such as drag force and the tracking of mass that may have caused this. Thank you.